Okay, so today is lecture 2, and its title is definition of cluster algebra and, if time permits, I will talk about Lorentz phenomena. But let me first start with the definition. And definition is, how to say, it's not the first definition which you imagine when you start think about these things. So just be prepared. Take some. I will. Okay, so for the first part, I will have some written slides. So the definition which I will give is not the most general definition which exists in this theory. So I restrict myself to the case which is called geometric type. It means that we don't have just matrices, but they will be geometric, so they will be encoded on quivers, oriented graphs. And similar to the story of, I don't know, Dynkin diagrams, you know, there is simply laced case where Dynkin-Cartan matrix is symmetric, and so-called symmetrizable case, which is not simple laced. And I restrict myself to symmetric case. So whatever, so definition which I'm going to give and which I'm going to use during the course will be not the most generic one. So at least two such restrictions, and actually more. The key definition in this theory is a definition of the seed, not actually two key definitions. One is the seed, and another is mutation of seed. And seed is a data which consists of pair. It is a certain combinatorial data and algebraic data. And combinatorial data, it's antisymmetric matrix Bij. This matrix of the size n times n. There's some number which I fixed from the very beginning. We have defined cluster algebra of rank n, and in particular it means this matrix antisymmetric and integer. All these numbers are integer, therefore they can be, this matrix can be encoded as in terms of quiver. So quiver is a oriented graph which have the n vertices, and Bij is the just number of edges from I to j minus number of edges from j to I. And we assume that this graph has no loops, so the edges is grown from vertex to itself, and has no two cycles, pair of edge in with opposite direction. Of course, theoretically speaking, one can add such things, but they do not affect the matrix Bij. So one can safely assume that there is no such cycles, one cycles and two cycles. So this is geometric data, quiver, combinatorial data, and algebraic data is n variables, which I decided to denote by capital A, A1, AN. And for each vertex, we assign variables. To be more accurate, one should say that this is not just variables, they belong to a certain ring. I ignore this. I'm not very accurate. Okay, this is seed. And the next definition is the definition of mutation. Mutation can be performed in vertex of the quiver, so any number from 1 to n. So mutation k in vertex k, it's under the mutation we have some transformation of the combinatorial data and also some transformation of the algebraic data. First, let me explain transformation of the combinatorial data. So it is written in terms of the matrix. So we have new matrix which denote B prime, and for the rows and columns which number k, we just change the sign. And for other Bij, we have this term. which is maybe not most, okay, maybe not very clear. And instead of explaining this formula, I can make it like I will explain that what does it mean geometrically in terms of queer. But let me just let me first explain geometrically, and then I return to this formula. So geometrically, this algorithm is performed in 3 steps: 1 to 3. First, we inverse all arrows at the vertex k. So, for example, I draw it here. I assume that we have, say, 3 arrows, and we inverse all of them. Step 2, we complete 3 cycles in the middle of the vertex k. So if after this reversion we have this arrow from I to k and arrow from k to j, then we could just add one more arrow from j to I. And last step is delete 2 cycles. So theoretically speaking, could be some arrows in this direction before mutation. Then if we add arrow in this direction, they cancel each other. Okay, this is the algorithm. Okay, it needs some time to live with it to get.
About the second, may I ask you a question? When we do the second step, we use arrows which we have after the first step, yes?
Yes.
Mm-hmm.
Let me a bit explain this formula. So we get extra term, which which correspond to, we have 2 edges from I to k and from j to k. So this first row in this formula, each correspond to step 1. We inverse all edges which are incident to k. And now this term, this correspond to exactly these triangles. And you see, if BAK and BGK have the same sign, then these 2 terms are equal. So it doesn't matter which of the b's you take absolute value. So this is 0. It means that if we have arrows in the same direction, we have no triangle and no additional term. But if signs are different, then we add exactly BAK times BGK arrows in the correct direction. So if
could you, excuse me, and could you complete the example about this D2? Like which arrows should we add?
So in this case, we add such arrow. I asking here. If we start just from the I mean, here I didn't. I mean, this is a star of the vertex case. In principle, there could be more arrows and so on. But if we assume that this is all what we have D4, then we should add this arrow and this arrow. Okay.
Mm-hmm. Okay. Thank you.
Okay. So this is a definition of the mutation of the mutation of the combinatorial data, and mutation of the algebraic data is more simple. It's given by we should assign new variables to each vertex, but it appears that first maybe I should write that AJ prime is equal to AJ for G is not equal to K. So the only variable which changed is a label which lives in K's vertex. And for this vertex, we have the following relation: the product of a K prime and a K is equal to binomial. And now how this binomial looks like? First, we take the product for all vertices A such that arrows goes from I to K. So this I to k arrow, in other words, means that this what. Let me make the formula larger. It means that this number bk is positive. And then we add the sum, the product over all bk for which bk is negative, or maybe 0 if it doesn't matter. And here we again have a now in positive power, which is now minus bk. So we look to the in this example, the new vertex will be product of these two plus this one over the old vertex k. I will show it. Okay, maybe. Yes, I mean, I plan to give more involved example, but let me even this right. So, okay, so if we start from this one, maybe I can copy. Okay, and then, as I said, we will have two more arrows and a new vertex. Okay, let me label not by k, but just 1, 2, 3, 4. 1, 2, 3, 4. And a2 prime is equal to a1, a4 plus a3 over a2. Okay. Maybe it should be noted that if there is okay, I wanted to write some lemma, but maybe it's too early. Maybe I should first give a remark. If we have vertex, if okay, let me move lemma. If vertex k is sinc, it means that we have vertex and all edges to it just go to it. Then uk reverse orientation. At edges adjacent to k. And new variable ak prime is equal 1 over ak, and here will be 1 plus some product. So we have no edges ongoing from k, then one of this product is empty product, and empty product is equal to 1. Okay?
Okay.
Okay. This is straightforward to see that any mutation squares to identity. It means that the matrix returns to the same matrix and variables are returned to the same. For the matrix, for the quiver, I mean, we do the same steps. So first we reverse all edges, so return them back. And then if we hit here, we have such triangle, then after the reversing, we have triangle in the opposite direction. So these edges will also cancel. So, and for the variables, you see that the sets of vertices which are adjacent to k, it remains the same. Their roles are interchanges, that the edges from which we have edges from which edges goes to k, now they have opposite and vice versa, but it doesn't matter. Again, we have some of the same two terms. So each mutation squares two identities. Okay. Okay, now let me spend some time on example. I start from probably the simplest example, simplest, a bit non-trivial example, but anyway. Let us take this quiver and assume that variables are equal to a and b. What? I don't know whether I have some better notations. Maybe not. Okay, so now we will do mutation. First, let us observe, and this vertex number A is this vertex number. Maybe better to label them. I don't know. Maybe better to label A1 and A2. Let's do some mutation. For example, let's do mutation mu1. What kind of quiver do we get?
The arrow will be in other side.
We get the same quiver, but with opposite orientation. Yeah. Actually, it's easy to see that if you change all orientations, then this sort of, I mean, this changes in whole orientation commutes mutation. Okay, and what happens to variables? Then here we have A2, and here we will have 1 plus A2 over A1. Now let's mutate more. There is no reason to mutate in mu1 since we just go back. So we mutate it at mu2. What do we get? We get the quiver just returns back. But what happens with vertices? So this vertex, this variable is the same. What do we have here? We should take 1 plus that number and divide. So what do we get? We get 1 plus A1 plus A2 over A1, A2. Is it correct? I hope so. Then we do one more mutation. Which mutation should we do? Who is here?
No, mu1.
Yeah, yes, mu1, mu2 have will just return us back. Quiver change the orientation. One of the variables remains the same. And now let's compute what will be the first variable. So what should we do? We should take 1 plus this fraction
divided by A1.
divided by
1 plus A2.
Okay, let me do this computation using another color. It will clear that it's something temporary. Okay, this is quite now we rewrite this fractions, and you see in the numerator we get just 1 plus A1 times 1 plus A2. So this is some sort of good news. we get just one. So the final answer is simpler than it maybe expected from the first glance. We get 1 plus a2 over a2 over a1. No, we get 1 plus a1 over a2. So this actually is a term like we had before, but now a1 and a2 changed. Okay.
It means that if we go, we make mu2, we will have the first. Yes.
And actually, it means that now we will go, we will somehow go the same direction, but now the situation will be simpler and simpler. So now we do mutation mu2. We get quiver at the beginning. Which variable? So here the variable will be this one, and what will be here? No, we can compute. So what we do? We have 1 plus a1 over a2 over 1 plus a1 plus a2 over a1 a2. And if you compute the get the numerator and denominator, then on the upper hand we have this, on the low this, and then we get just a1. And this is expected. So if we do mu2 from here, we get one variable a. Then similar, if you do mu2 here, we get this variable. And at last, if we do one more mutation, now what remains? Mu1. And then we do, what do we get? We get again the same clear up to reversing orientations, and the variables will be here we get a1, and here it's quite straightforward to get it. So what is the result of all these computations? That actually these transformations are not how to say. So we come to the cycle, we obtain some periodicity. So the composition of 5 mutations give us the same variables as at the beginning, but just up to reversing orientation. In particular, it means that if we compute 5 more mutations, we get exactly the same quiver as our starting quiver. And in this case, there's no other direction. This is all what we can get from the start. But I would say that we get 5, which is probably from the first class could be somehow unexpected. Why 5? So periodicity, maybe it's okay, but why period is equal to 5? This should, if somebody heard about some pentagon relations, and such stuff, it is actually related. Questions about this example? Okay, let me briefly show you another example. The same, but now we have two arrows. And initial numbers n1 and 2. I will not write so many times the same quiver, so quiver remains the same. The only we have just to compute the value of the variables. So first one, if we do mutation in say a1, then the second variable will be a2 squared plus 1 over a1. And then the picture continues. So we take the square of the variable plus 1 over the previous. So the variable, so one can think that the variable satisfies the recursion relation. Zk plus 2 is equal to zk plus 1 squared plus 1 over zk. And let me recall you that actually this relation was mentioned on the last week. So if you substitute first numbers equal to 1, then we get 1, 1, 2, 5, 13. Then I don't know. Difficult. 34 and so on. So these are Fibonacci numbers. In particular, in this case, we have no periodicity. In variables. So the quiver remains the same or just inverse orientation. So up to automorphism, you have one quiver, or if you do not allow permuting vertices, you have two quivers. It's not big deal. But there is no periodicities in the values. You see they grow and just like this. So the case where we have one arrow is special, but it is the simplest case, but it's quite special. Okay, now let me study more involved example, which is actually which we discussed mostly on the last time. This example will be related to triangulation of the convex polygon. So we have triangulation. And now in this triangulation, starting from this triangulation, we construct a quiver. So in each triangle, sorry, my triangle appears to be not closed. In each triangle, we insert, we put vertices on its sides and orient it clockwise. So starting from triangulation, we assign vertices to each diagonal used in the triangulation and each side of the triangulation, and assign the vertices like this. This is how we construct quiver, and this combinatorial data for the seed and algebraic data. So if we have some HAB to it, we can assign PAB.
Sorry, what are the orientations?
I draw the quiver, and so in each triangle, to each side or diagonal using triangulation, I assign the vertex, and then on each triangle, I draw edges clockwise.
Oh, thank you.
So I somehow fixed the orientation of the plane. And further, if this picture will be drawn not on the plane but on some surface, this surface should be orientable. And actually, we pick some orientation. Okay, so this was the combinatorial part, and algebraic part to each HAB we assign PAB. Let me recall that last time we have some space AN, which is a space of matrices 2 times n. Space of matrices quotient by SL2, and PAB is just 2 by 2 minor of this matrix. And what we discussed is this PAB, which are for given triangulation, PAB assigned to the edges of this triangulation are local coordinates on this space AN. And now I'm saying that they're not just local coordinates, but they're cluster coordinates, if you want, which correspond to the certain seed. So to any triangulation, we assign a seed. I draw you a quiver, and I draw you, and I specify variables. And flip of the triangulation, flip is the change of the, if you have a square or I don't know, rhombus or whatever, it can be divided into two triangles in two ways, and this flip of this diagonal changes triangulation and changes the quiver. Observation that this change is actually the mutation of the quiver. So first, it should be seen combinatorially. So we do mutation clearly in this vertex. So we change orientations on the vertices on the edges which adjacent to this vertex. And after that, we have to, close triangle, so add such edge, and also close triangle and add such edge. And here we have cancellation. We have this edge is cancelled with U1 and this is step 3, and similarly. In terms of now, let me state this. Observe that in terms of the variables, what do we have? We have Plucker relation, which says that if here the value of the variables will be like a, b, c, d, and diagonal is x. Here again a, b, c, d, and now the diagonal is y. Then Plucker relation says that x times y is equal to ac plus bt. And this is exactly mutations which we defined. So to each triangulation, we assigned a seed, yet it appears that change of coordinates which correspond to flips, which we discussed last time, are just mutations under our current definition. This K observation. So to each triangulation, we assign a seed where variables belongs to the ring function of this space AN, to this cone on the Grassmannian. And this assignment is consistent with definition of mutation which we given before. Okay, are there any questions? Okay, let's look a bit more on this example. Okay, let me move it a bit down because I have space, and this is actually new topic. That in the construction above, we looking more carefully, we actually have two types of vertices. When we mutate only in diagonals. We cannot mutate in the sides. And this is somehow typical story. So quite typically, when people study some clusters, some seed, some of the vertices are called frozen. So it means that we cannot mutate on them. And some of them are called unfrozen. So we can mutate. I usually use notations that we have n frozen and then total m variables. So number n unfrozen and total number of variables will be m. So we have m minus n frozen variables. It is, I mean, this maybe should be put as a remark, just not completely obvious that if we have that if we mutate only on unfrozen variables, then ages between frozen vertices don't matter at all. So, because if you define new variables and if you mutate in the unfrozen and you look at only on the ages from unfrozen to other, and if you look to what happens to this quiver, also this part which goes from unfrozen to unfrozen or unfrozen to frozen, it doesn't affect it by vertices between frozen to itself. So actually, it is important only to look to the rectangular matrix n times m. So when everything is defined in terms of the rectangular matrix, it means that some of the vertices are frozen and edges between them do not match. This is a technicality, but quite often used. For example, in the example which we discussed, some of the vertices are frozen. We can mutate in any diagonal, but what does it mean to mutate in the side? It is unclear. Okay, now in case of GLN, we have okay, the idea I have put now the answers is the clear of finite type, but let me but before this. So what we have? So first of all, how many variables we have? Okay, let me move it a bit higher because maybe I want to add much more. So first of all, we have triangulation of n gone. So we have n frozen and n minus 3 unfrozen.
Sorry, I want to ask, what do you mean by the height of Grassmannian 2n?
This is a fine cone of a Grassmannian. So Grassmannian 2n is embedded in the projective space via Plücker embedding, and we consider the set of the corresponding lines. Probably.
Okay, thank you.
And actually, we can see we are more interested in not this manifold itself, but in spatial functions on it. So this is the set of spatial functions. This is the homogeneous function of the Grassmannian. Another way to say it, the set of functions, it is functions on this space of matrices which are invariant with respect to multiplication by L2. And this algebra is generated by P's. Anyway, so this was part of the previous lecture. Maybe you can, I hope you can follow those notes. If not, then ask me, I will give you more references. Anyway, so for GLN, we have unfrozen, minus 3 unfrozen. And if we mutate on any unfrozen variable, we again come to, and we just change the triangulations. It means that in this case, we have finitely many possible seeds, because there are finitely many triangulations. So in this case, number of seeds is finite. And also number of variables is finite, because all variables are just some Plücker coordinates. Of course, in this case, it is we can say more than just the statement about that something is fine. We can compute number of variables, its number of sides and diagonals then gone. So it will be what? N times n minus 1 over 2. And number of seeds is the number of triangulations. Who knows what is the number of triangulations of the n-gon?
The Catalan number.
Yes. Cn. Catalan. Of course, then leads some to very interesting combinatorics, which I actually skip in my course. But as a result, let me state that this is an example of so-called quiver of the finite type. Quiver for which we can get finitely many seeds. In our examples above, this quiver was of finite type. So after the 5 mutations or 10, whatever, we actually get the same seed as before. But this quiver is not of finite type because we have finitely many values of the variables. And we have infinitely many values of the variables. The fact that this finite type is not actually the new, how to say, because you see from the Grassmannian, we see actually easy to see that quiver. Maybe gain a bit more space. Write it here. Quiver for this algebra, which we consider a fine cone of the Grassmannian to n. In order to write down the quiver, it is useful to choose some very simple triangulation. I mean, the quiver can be arbitrary, but if we choose triangulation like this, then for the unfrozen vertices, we get just the linear quiver. Which can be defined with the oriented it is oriented Dynkin diagram for a n minus 3. We have n minus 3 diagonals, and at least if we choose triangulation like this, where all diagonals goes from one vertex, then we get the edges of the between corresponding vertices just form a chain. So the quiver from which we started, where we have only one arrow, it actually corresponds to triangulation of the pentagon. And this is why everything becomes periodic after 5 mutations. So after 5 mutations, so each mutation just changes the triangulation, and after 5 mutations, you come to the triangulation from which you started. So everything, you get what you have at the beginning, up to the mutation. This is why we had 5. The only difference that here, for computation, I assume there is no frozen variables, and here we actually have 5 frozen variables. But periodicity holds anyway. In both. Here we compute it without frozen, here it's frozen, but periodicity holds anyway. Actually, I put it as this as a problem. So there are some problems now. I mean, after the definition, one can invent a lot of exercises. And according to exercises, this lecture will be maybe the most dense. So for example, one can prove that in any whatever frozen variables are, if you have two variables which are connected by just one arrow, then composition of these two mutations. Okay, so this variable, this vertex I, this vertex k, then composition of this product of these two mutations or in power 5 is identity. Or if you just compute mu I, mu k, mu I, mu k, mu I, you just reverse x and y. And in principle, it says, so it means this is true, whatever other vertices are, how they're connected to k, to psi k, doesn't matter. So you can safely assume that all other vertices are frozen, and actually edges between them are not important. So you can assume that you have just one frozen arrow vertex, which I wrote here, and compute for it. So this is actually a hint how to prove this problem. And if there is no arrows between x and y, then the situation is even more simple. Mu I and mu k just commute. So in other way, you can write that mu I mu k in power 2 is equal to identity. Okay. Okay, here is one more problem which says that if your quiver is a tree, some orientation of tree, then actually nothing depends on the rotation. You can use mutation to construct arbitrary orientation. And the last problem here is for one more quiver. Actually, this quiver from which we started is D4, to show that this quiver is also of the finite type. And actually, the variables are in natural bijection is with almost positive roots. By word almost positive, I mean that it is positive, and minus negative, I forgot to write, minus negative simple roots. And there is natural bijection for which you should look to the denominator of the corresponding variable. And from the denominator, you can somehow specify the root. So initial root variables, they correspond to some sort of simple roots, technically minus simple roots. And all other variables which we can obtain, they correspond to positive roots. In particular, in this example, which corresponds to A2, what we have 5 variables: A1, A2, 1 plus A2 over A1, 1 plus A1 over A2, and something over A1, A2. So these two can be viewed as in this bijection correspond to minus simple roots. These two correspond to simple roots, and this is the sum of two simple roots. All this story about roots for A2 for SL3. And the problem is to find similar corresponding, to check similar corresponding for D4 and for some other root system. Find integral. Okay. We came to some logic step. Are there any questions? Okay, now let me proceed further. And I want to return to the problem which I mentioned on the first lecture. It is about Soma sequence. So in principle, Soma sequence look like cluster story. So we have product. We have assume that we know zk plus 1, zk plus 2, zk plus 3, and want to find zk plus 4. Then we get a recursion relation. Then zk plus 4 times some old variable is equal to some binomial. That means that we actually have a quiver. Let's try. So we have 4 vertices. One, 2, 3, 4. Or maybe better write start from 0. Okay, maybe it doesn't matter. And we want, so assume that we have variables to each of these vertices, z1, z2, z3, z4. And now we want to define z5. And the recurrence relation has the form z5 times z1 is equal to some binomial. It means that we should mutate in the vertex number 1. And in order to have such a formula, we have what we have as a number of arrows from. We should have such story. So here should be 2 arrows, say from 2 to 1, and or maybe I prefer no direction. So I'm trying to check whether Soma sequence can be viewed as a particular case of the cluster mutation. We saw that for Fibonacci sequence. So it's natural to ask also here. Okay, so if it is so, then the curve should look like this. And we take the mutation v1. What then we get? We should reverse here all orientations. This we know for sure. But it appears that now here we should apply the same argument. So we should expect that actually Z6 is given by the same recurrence relation. It means
Sorry,
that
but you haven't reversed the Z4 Z1.
Maybe I made some mistake here. Yes, should be.
Yeah.
Here, the situation with the 2 should be the same as before. It means that now if I want to define the 6, it should be given by the formula like this. It means that I should have here such arrows which are goes in the opposite order. So in order to have that Z6 is equal to what is equal. Okay. What does it mean in the first picture? So after mutation, we have 1 arrow here. It means that before mutation, we had here what? 1. I realized that I missed. Yes, I draw this incorrectly because I mean, my recurrence relation is the following: Z5 times Z1 is equal to Z3, Z2, Z4 plus Z3 squared. So it means that here arrows should go like this, and here should be 2. Okay, let me change everything. Then after mutation, here should be like this, here like this, and here should be 2. And now the next recursion is the following: that this 6 times Z2 is equal to.
I think that the diagonal between Z2 and Z4 is not exist now, and there is the diagonal between Z3 Z4.
I mean, these two lines are not. We don't know them. We are now going to find. I mean, here from the recursion formula, I know these 3 lines, but know nothing about all the stuff. But for other stuff, I plan to use the fact that the recursion relation should keep the same. So it actually should mean that the curve more or less should remain the same after such mutation. And the same up to the cyclic permutation of the vertices. So now I should want to have that here the arrows goes like this. And here we have 2. So this is just 90 grades rotation of this picture, like this. So here we have had arrow from 1 to 3, and here we had arrow from 2 to 4 of degree 2. If it is so, then we can find the arrows before. So before here is still, I think we have the 2, and here after mutation we have here 1, but actually this 1 appears only after the cancellation. So here we should have here 3. And after mutation this vertex, we close 2 triangles, and instead of 3 we get 1. And now if we believe in periodicity, then here should be also 3. And here should be also 1. 1 is not necessary. So this is a quiver, and the statement is if you do mutation in the first vertex, we obtain the second quiver, which is related to the first one just by rotation. Then we do mutation in the second vertex, and then third, and fifth, and fourth, and so on. And using this way, we reconstruct Thomas recursion.
Excuse me, I didn't get how to write numbers like 2, 3.
2 is a how to say, it's valence of this 2 is the valence of the H. So it means that B13 here is equal to 2. Remember, we had quiver, but there could be multiple edges between 2 vertices. We have some matrix B, which counts the number of edges from I to J. Let's say. And this 2 means that we have. I can actually draw them separately, but I decided to just put valence near the edge. But this is not the number of vertices because I use another color. More questions?
And why did we get 3?
Here,
Yes.
Because after mutation, we should have 1 here, because it is related by, we had 1 here, and after rotation, there should be 1 here. But this 1 appears only after the cancellation, where we close 2 such triangles. So before it should be 3.
Okay, thank you.
I mean, there's some checks that using this argument, I reconstructed the query, but maybe it wasn't so obvious and actually shown that it is true that that all edges agree. So I checked only some of them, but it's true. So we get this funny quiver for which mutation 1 vertex now in first vertex is automorphism. It makes it quiver to itself. But of course, the variables are transformed non-trivially due to Thomas recursion relation. One can do the same for Thomas 5 sequence, and I left it as a problem. And now in the remaining, I don't know, 27 minutes, let me talk about Laurent phenomena. But before, maybe just a minute, I switch off the light.
Sorry, can I ask a question?
Yes.
It seems that first you complete triangles at Z1 and then you reverse arrows.
No.
As written.
I think no. Which arrow do you want to check?
For example, you had 3 arrows, Z3, Z2, but then we obtain just 1 arrow.
Yes, so it means that I first add reverse, and then I have 2 triangles to conclude. So I add 2 arrows in this direction, and they cancel, go from the 3 to 1.
Yeah, sorry, and then I just misunderstood what it means to complete a triangle. Thank you.
I think now it's clear, but just in case I show picture. So if we had arrow after first step, we have arrows like this and arrow like this, we add arrow, we close triangle. We make oriented recycle.
Yeah, now I see. Thank you.
More questions?
Okay. I didn't understand how we get from mutation Z1, Z5.
Maybe. So how do we get this formula?
Yes. We have like 1 plus product of Z2, Z3. Oh, sorry.
The different orientations. So we have Z2.
Okay. I understood. Thank you.
Okay, and now let me recall you that why we were interested in this Thomas sequence is because it is integer. So if we set all initial numbers equal to 1, then all result numbers are integer. And moreover, it is Laurent sequence. So if we all numbers, if it's set Z1, Z2, Z3, Z4 arbitrary, then all other terms will be Laurent polynomials with integer coefficients in Z1, Z2, Z3, Z4. And it appears that this is general phenomena for any cluster algebra. And I think I will not give a full proof in 20 minutes, but I'll start with the proof and hope to explain the main ideas. I will need some notations. So I will usually draw, I have a quiver which I draw in this color I'm not sure how it's called. Maybe I should, but maybe Beige. I don't know. So we have this color. Okay, I will call it beige, but not very strong. And use this color, draw curves, and also draw graph in blue. Like I try to write all numbers and variables, and this picture will the edges in this new graph will correspond to mutation. So vertices are seeds, and if two seeds t and t prime are connected by mutation in vertex k, I will draw edge between t and t prime and label this edge by k. In any seed, we can perform n mutations. N is the number of unfrozen variables. So we get some n regular graph. And regular graph where values of each vertex is n, and the edges which goes from each vertex are colored from 1 to theorem. And this theorem, as many in the story, is due to Fomin Zherevinsky. Is the following. So assume that we have some initial seed T0 and perform D mutation, T0, T1, and so on, Td. Then variables which correspond to the final seed Td are Laurent polynomials on the variables on the initial seed with integer coefficients. Okay, now we're going to prove it. I will use notation, so I denote the variables on the initial seed by A1, A. And the proof will be performed by induction on D. Base, one have to check D equal 1. For D equal 1, we have T0 mutated in some vertex, say, G. And what you get new variables, say AG prime, which is equal to sum of two monomials, M1 plus M2 over AG. And clear, this is a Laurent polynomial. We don't have actual denominators. So this case is trivial. We will also need for base d equal 2. So we have two mutations. First, say in vertex j, and second in vertex k. If j is equal to k, then we just return to the initial case and everything is, and the variables of t2 are equal to the variables of t0. If j is not equal to k, then we get two new variables. Then when after the first mutation in T1, we get some variable AG prime, and then if we mutate in K, we get some new variable AK prime. But this variable AK prime will be equal 1 over K, and sum of two monomials, M3 plus M4. Where this M3, M4 are monomials on all other variables, in principle, it could include AG prime, but AG prime only in numerator, not in denominator. So this is again a Laurent polynomial. Okay. Okay, I hope so. Now let's do step. And step goes from the assume that we proved everything for the such sequence of the length d less than d, and now we are going to prove to the sequence with length d. Here again rewrote the sequence and keep my notation. So the first notation which I use here has number g, and the second notation number k. And there are the proof consists of two cases. One is more simple, and another is less. First case is assume that G and K are not connected. So it means that in the original incidence matrix for zero seed, BGK is equal to 0. As we said, if two vertices are not connected, then mutations in them compute. So it means that we can add one more edge here, T1 prime, which is connected with this vertices permutation in the opposite direction. The set of variables for T1 is original set of variables, but we have new, after mutation G's variable, we have new J's variable. K is the same, and yeah. And this J's variable is equal to some sort of sum of two monomials over AG. And variables for T1 prime A1, AK, AJ, AK prime, AM, and here we get AK prime is equal to M3 plus M4 over AK. Now recall that we are using induction, and the distance from T1 and from T to TD is less than D minus 1. So we can use induction conjecture. It means that we know that A of TD by induction A of TD Laurent polynomials on A of T1. On the other hand, there is another path of the length less than D. It is a path from T1 prime to TD. So similarly, they are Laurent polynomials on T1 prime. So any variable on TD is some Laurent polynomial here and here. So what could be on this any variable here is some rational functions on A1 AM. What could be in the denominator? We want to say the denominator is monomial. From this, it follows that on the denominator could be some factor of M1 plus M2 or monomial. And from this argument observation follows that in the denominator could be only some factor of M3 plus M4 times monomial. So if monomials M1 plus M2 and M3 plus M4 are coprime, in ring of functions on A1, AM, then we are done. Of course, here I use the fact that the ring of polynomials is a unique factorization domain. It is quite natural to assume that if you have just two monomials, that they are coprime, but there is a problem. Generally, this is not so. Generally, it could be not. It could be not true. For example, it could be that that these vertices, you see, M1 and M2 is M1, the first monomial is responsible to the G's row of the matrix B, and second from the K's row of the matrix B. It could be that these rows, for example, coincide. So it means that it could be that M1 plus M2 is just equal to M3 plus M4. So we have two vertices which are just the same, which have the same adjacency. So these polynomials coincide. Or it could be that M1 plus M2 is some M3 cube plus M4 cube. So one of the rows is 3 times another row. It's again, these two binomials are not coprime. So we are almost done, but actually not, because argument could fail. Okay, so this is a problem, and I will supply it. And how to solve it? There is a following trick. Solution. We add new frozen variable. It isn't necessary as it's frozen or not, but we will not notate it. So, new frozen variable, which is connected to, which makes a difference between J's and K's vertices. So we have some pair vertex J, and we add frozen variable of the number m plus 1. I put it in square, represents it as frozen, and it is not connected to vertex K. Then, instead, before we had M1 plus M2, and now it transforms to M1 AK, A M plus 1 plus M2. And M3 plus M4 remains the same. So in terms of the polynomial AM plus 1, this polynomial is linear function. If you put all variables equal to 1, it's just AM plus 1. So it is an irreducible polynomial. And this is a constant. So these two polynomials are coprime. Hence, so we add this additional variable. We get the fact they are coprime. Hence, for this new quiver, new extended cluster algebra, we have Laurent property. So we have Laurent for extended. But then we can send this set this variable, new variable equal to 1, and restore the formulas for original quiver. And if you have a Laurent polynomial and set some variable equal to 1, we again get a Laurent polynomial. So the consequence, we get Laurent for original quiver. So we are done. Okay, I have like 5 minutes for this second step, but are there any questions? This about the logic of the proof. Okay, if there is no questions, let me say briefly how the proof goes in the second case. So okay, now I have actually have space here. So case 2 is this number is now not equal to 0. Without loss of generality, I can assume that this number is negative. Let me again draw our tree, I mean our graph, which okay. Doesn't matter. Maybe it's not important now. And in the end we get, so we have T0, mutations J, mutation K, here T1, we have here T2, and then we have TD. Now we cannot argue like here, so we cannot produce T1 prime just another way, intermediate step here, but anyway we can do mutation here in the vertex J and get something which I still call T1 prime. So concerning to variables, so anything was changed is variables in the number J and K. So here we had AJ, K, the original. On the T1 we get maybe not sufficient place, and maybe to make it more clear, I use another color. So here in the beginning we had AJ, K. After first mutation, we change the first AJ prime and the K remains the same, then we can change both. And again, after mutation G, AG changes one more to some AG prime and we get K prime. So argument will be the same. So we get two directions to TD. One starts from T1, another from T1 prime. But now this the corresponding variables differs on two positions. Here we have AG prime, which in principle can lead to some denominators non-trivial. Here we have AK prime and also EG2 prime. It appears that for EG2 prime, we don't even know that this is Laurent polynomial, and this is lemma 1. The proof of this case is based on two lemmas. First lemma is to show that AG2 prime is Laurent polynomial of these variables. This is a computation, which I'm not going to do now. It can be found in literature. And in some sense, this can be viewed as a extension of the base of the induction. So when I started from induction, I showed that I should prove for d equal 1 and d equal 2. So actually, it appears that somewhere inside the proof, it appears that I should also specially consider case d equals 3. G. And this is a computation. Okay, you proof. Okay, I will do it now. And after this computation, you can argue like before. So by induction, you can just repeat this argument. And it remains to note that the AG prime is co-prime with both of these polynomials, AG2 prime and AK prime. Then I use the same argument that there's no new poles in denominator. But in principle, this could be false due to some coincidence and so on. And this is solved by adding frozen variables. So we had two frozen variables as before. So here we get one variable connected to J. Now it will be not sufficient. We add one more connected to K. Then we have number n plus 2. And after that, the following lemma holds. AG prime is co-prime with AG2 prime and AK prime. So the new variable which we get in seed T1 is co-prime with new variables which we have at seed T1 prime. This is proven. Again, I'm not going to explain the proof since almost out of time. It is proven in the, okay, I'll give a reference in the Zelinsky paper. It's just careful computation. And hence, in the denominator, in the formula for rational functions of the variable of the final seed, we cannot have non-trivial denominators. And the theorem is as an application of the theorem, I put a problem which allows you to show that the Laurent phenomena holds not only for just original Summa sequence, but if it add coefficients to Summa sequence, everything still holds and Laurent phenomena still holds. Okay, I think it's 12 in Moscow, so time to stop. Are there any questions?
In the simplest case, how precisely you modify the quiver? I didn't understand.
I added one vertex. Orientation is not important. I added one frozen vertex which is connected to J and not connected to K. After this, the rows J and K in the matrix become different and not proportional.
So it changes mutation in J. Okay.
This changes, I mean, when we mutate in J, so instead of sum of one of these two monomials, will have additional term factor am plus 1. Now these two polynomials become coprime because one of them is linear on this new variable and another is constant in new variable. Okay, if there's no more questions, let me